There are three ways that we can do heating, that we can, um, by exposure to heat, change the temperature of a sample or a system that we're talking about. The first one is, and it's the one that we've already seen, we can literally put our thing in contact with a bath of ice, in contact with a flame. We can get the heating to happen through contact, through conduction. Let's define a rate at which we do heating. Q, remember, is the quantity of heating. How much are we doing every unit time? One way to think about this is like if you've got a Bunsen burner or something. If you, or a burner on a stove, if you turn up the flame, then we're doing, in the same amount of time, we're doing more Q. So we can talk about this. Let's define it as capital H, heat flow or heat current, like electrical current. We're moving the heat is doing at this rate, where we are heating so and so much every second. For conduction, we need to know a couple things. We have exposed our thing, our object at some temperature. We have exposed it to a, let's say that our thing is cold for now, and we've exposed it to a hot thing, the flame from the burner, let's say, or the, if it's a coil stove, right? And it's the coil that is hot and the pot is actually contacting the coil. So how different are those two temperatures, right? How forceful is this gradient, the gradient in temperatures? Is it a very steep gradient such that, like, if we're going to let heat flow down the gradient, is it going to want to flow quickly because it's a very steep gradient, or is it going to want to flow less quickly because it's a more shallow gradient if the two temperatures are about the same? How far does it have to go? Used capital L a second ago, so I'll just use a lowercase l. The longer the path that we need, if you have your cooking pot, you're boiling pasta, water to make pasta, the wall of that pot is relatively thin so that we can conduct the heating through from the burner to the water in the pot. If we used a big hunk of aluminum, it would not travel, the heat current would not be as large because it's got to go through that large distance of, aluminum cook pot, as opposed to a thinner distance. So the distance between those two temperatures, and it's really this that we're going to call the gradient. How much temperature change over how much space? Think of this like fluid flowing in a pipe, I guess. We've got two pressures, one on one side, one on the other side. There's got to be a positive pressure gradient to push us through. And we care how long the pipe is. We also care how wide the pipe is. What's the diameter of that pipe? We're going to be able to move more heat through this much length if there's more contact, right? If the area of contact is larger. And there's the last piece is a parameter K that has to do with how good a job a particular material is at transmitting heat by conduction. So that's a constant that depends on the material that we're trying to move the heat through. And then we can look that up in a table. Okay, remember again, so we've got the cross-sectional area, the area of contact, how, through what distance and what temperature differential, what is the temperature gradient, temperature change over the length across which that change is occurring. Okay, let's take a look at some slides. Suppose we've got some material with a cross-sectional area A. We are communicating heat current from TH, a hot temperature, to a cold temperature, like we just talked about. If we double the cross-sectional area, then there's twice as much ways for us to do heat current. So we end up with twice H. If we make the path longer, then we have made it harder. We've decreased the temperature gradient. Every millimeter along, the temperature isn't changing by as much, so it's not as forceful a heat current. There isn't as much, and it'll take longer, right? We're moving generally less Q per T because H is going to decrease. That's one way we can do heating. Another way is by actually physically moving hot fluid from here and putting it over there so that now the temperature of that region is hotter than it was. And this sort of motion within a fluid, and it's really nice to have the word fluid, because this sort of thing happens in liquids and gases. This flow of hot fluid to a place where the fluid is generally colder, and we can heat that region by actually taking a bunch of hot fluid and putting it over there. That's what we're going to call convection. There's no good equation for that, so I'm just going to put it up here in the corner. Convection, when you think about convection, think about the rolling boil that happens when you're boiling water for pasta. Think about wind. That's really what's happening, is that we've got a quantity of air moving from here to there. The third way to transfer, the third way to do heating via heat current is by radiation. An object at a temperature emits radiation according to a formula that I'll write on the board as soon as I stop sharing the screen. So we've got, let me say this again, we've got conduction. We're actually putting the two temperatures in contact with each other. Convection, where we're moving the material from one spot to another. And radiation, which can happen at a distance. They don't have to be in contact. And there actually doesn't even have to be anything between them. A lot of the heat current coming to the Earth from the sun is as a result of radiation, because well, gosh, in fact, all of it, right? Because it's not actually in contact, and it's not convection. There's no fluid moving because it's, space, it's a vacuum. All of the heat current from the sun to the Earth is as a result of radiation, and that's the next thing that I'll write on the board. That little note up here, we've got this fraction that we're going to call the temperature gradient. Just so it's still there. If If we want to talk about radiation instead, then again, we need to know the area of the surface that is emitting. We need to know its temperature. And we need to know, kind of like conductivity, how good a job does this thing do at emitting radiation? I want to get the formula right, so let me just look it up really quick. Yeah, I see. I thought there were two. Lowercase e for emissivity. How good a job at emitting radiation. And there's one more parameter that I'm going to put on the back. It's a constant that we need in this equation, and it's the Stefan Boltzmann constant. Well, we'll represent it with a lowercase sigma. It's like an O with a tail. And it's got a value. We can look that up. It's not a huge thing. We can just go look that up. The emissivity we look up in a table as well. So that's how good a job. So that's the heat current that results from radiation from a surface of area A that is emissivity good at emitting radiation at some temperature T, and then the Boltzmann constant. Now, I guess I like to think about, like, I radiate energy, but also so does the wall, so does everything, right? And I'm in the way. So all of my surroundings are also emitting radiation, and that radiation is coming towards me, and it's sort of like, well, if if I can dish it out, then I can take it just as well. The emissivity kind of works both ways. There's an absorption that goes along with the emission. It's a matter of what is the temperature of the surroundings. So if we wanted to talk about like the net heat current of a thing in an environment at a temperature, we were going to have to subtract the emissions, the radiation that object receives from its environment. So actually, well, I don't know. We can leave it there. But the net heat current, I'm just going to put net H. The object at some temperature, and how is it absorbing with the same parameter emissivity? It's also like absorptivity, the temperature of its surroundings, still to the fourth power. And that's like, well, that's like a human existing in most environments, unless it's summertime, right? So like my body temperature is, I don't know, 37 degrees Celsius. And I'm existing in a room with a room temperature of something like 20 degrees Celsius. So as I radiate heat with this heat current, I also absorb from the room, which is at a slightly colder temperature. So the net heat current is away from my body. Cool. Okay. That's chapter 17. I'll end this segment there.